Yeah, so welcome to the next class, and as in the last class we have just gone through the field introduction to the field evaporation, which consists of both field ionization and the desorption of atom from the tip surface. So I'll just briefly go through again the revise for at least 2 to 3 minutes. So in the screen you can see that the atomic structure, where there is one atom is protruding, and this is with no field. This is with no field. Okay, so if you see the potential curve for this particular protruding atom, you can see that the potential energy curve corresponds to this blue line. Okay, and this has a certain binding energy. Fine. Now if you think about ion, which is where the some number of electrons have been drained out, then the ion potential energy curve will shift upwards. Okay, so that is related to the number of electrons which has gone drained out, which is related to the ionization energy, and as these electrons has traveled as drained into the structure, so there will be a negative of the work function depending upon the number of electrons. So you will have a total theta q0, which is a energy barrier. Okay, so this is with the no electric field. If you apply an electric field, okay, so what will happen? The first thing will happen is field ionization. Okay, so your electrons gets drained out towards the tip, towards the lattice, toward the tip. Then the protruding atom will gets ionized depending upon the number of electrons which are drained out, and usually what will happen in presence of field, they will accelerate, and due to which on application of the field, what will happen, their potential energy curve will be distorted. Okay, so previously the potential energy curve was like this. Now on application of field, it get distorted. Okay, and it will develop a energy barrier, which is nothing but a hump or Schottky hump or Schottky barrier. Okay, so the two important things. One is by applying the electric field, what we are doing is the reduction in energy barrier can takes place. So this energy barrier is a direct function of electric field applied. Okay, and also when there is a Schottky hump, and when there is an energy barrier, due to the thermal activation, the ions can overcome that energy barrier and can accelerate towards the fluorescent screen. Okay, so this is the assumption that only thermal activation is considered. At low temperatures also tunneling can occur for the acceleration of the ions along the field lines. Okay, now we'll go through some of the basic equations which can okay. So now we will just go through the basic equations which can describe the energy barrier. So first we will talk about energy barrier. Or it can be related to the height of the barrier, which can also called as Schottky barrier, Schottky hump. Okay, so this is termed as QF. Okay, so this is nothing but a superposition of charge image potential. Means I am talking about the ion charge image potential and the potential of the electric field. Okay, so this is nothing but the superposition of charge image potential and the potential of the electric field. theta f is given by theta 0 minus under root of n cube E cube divided by 4 pi epsilon naught f. Here f is the field and E naught or the epsilon naught is the dielectric permittivity, dielectric permittivity of the vacuum. Okay, and other terms are the number of electrons and E is the charge. Okay, and Q0 as I told you in the last class, you will have a, for an atom, this is for an ion, Q0 is the total energy barrier. Okay, so when you apply an electric field, this field line, there will be energy hump, and this particular hump is called theta f or the Schottky hump, and this theta f is given by this particular equation, and which is a function of electric field. Okay, so it function of electric field means you can increase the electric field such that you can get theta f is equals to 0. The energy barrier is 0. When the energy barrier is 0, then what we call that particular field is called the evaporation field. Evaporation field of that particular element or the needle, evaporation field. Okay, remember when theta f, the energy barrier is a function of the electric field which is present just ahead of the tip surface. When this electric field is sufficient enough that your theta f becomes 0, then the field is called the evaporation field of that particular element. Okay, so the another term which is important is evaporation rate. Evaporation rate. And this evaporation rate can be, to understand this, first we need to understand the probability which is PEVAF, probability of field evaporation. Probability of field evaporation, and as I told you, this particular field evaporation model by Mueller, it's usually is assumed that this is thermally assisted process. Thermally assisted process. So due to this thermal nature, what we can do is we can actually write the equation based on Maxwell-Boltzmann equation, and it can be written as the P evaporation is proportional to exponential of minus theta f, which is a energy barrier, divided by kBT. This is why we call it as a thermally activated process. Okay, so this is given by Maxwell-Boltzmann equation. Okay. Now, in that Boltzmann equation, theta f, QF is the energy barrier, and we have seen that energy barrier is a function of the field which is present, correct? Kb is the Boltzmann constant and T is the temperature, absolute temperature. Now, when there will be a thermal agitation, then there will be a vibration of atoms at the tip surface. Okay, so this vibration will have a certain frequency which is given by v0. Okay, this is the frequency of atomic vibration, frequency of atomic vibration perpendicular to the surface. Okay. So, due to the thermal agitation there will be a vibration of atoms, and they have a certain frequency which is given by mu 0. So, combining mu 0 and the probability of evaporation, you can get the number of atoms which are field evaporated per second. Okay. That can be given by Arrhenius equation. Okay, that is equals to, this is the number of atoms per second for the field evaporation, this is the frequency exponential of minus theta f divided by kBt. Okay. So, this is the evaporation rate, which is the number of atoms which is evaporated per second. Okay. And this particular equation holds very good with the experimentally determined values. Okay. So, as I told you, even though we have even though it is neglected that the tunneling process does not occur, but the experimental values can be are easily matched with these values. Okay. So, this is the evaporation rate. Then this evaporation rate, the frequency. So, with experiments, Kellogg has by experiments on Arrhenius plots, actually Kellogg has estimated or is measured the frequency is in the range of 10 raised to power 11 to 10 raised to power 13 hertz. Okay. And depending upon the electric field, the theta f or the qf is almost near to the 1 electron volt. These are the experimentally measured values by Professor Kellogg. Okay. So, in the later song, what he has shown is the evaporation rate as a function of field. Okay. As you know that this particular evaporation rate directly depends upon your theta f, and theta or the qf, and qf is the energy barrier, and this energy barrier is a function of field. Fine. So, T Song has plotted the evaporation rate versus field, relative field. Okay. So, if you see the plot, which was made by Song, you can see this is the field and this is the evaporation rate. You can see that by changing a field at least a minimum of 5%, 5% field, the evaporation rate changes by 2 to 5 orders of magnitude higher. Okay. So, and he has plotted for different elements, and you can see that by changing a 5% field or increase in 5% field, there is a significant increase in the evaporation rate. It is almost around 2 to 5 orders of magnitude. Okay. So, now coming back to the evaporation field. Okay. So, as I told you that this evaporation field, we have a mu 0 exponential minus qf divided by kBt. Okay. It might possible that the electric field the electric field is, we made the electric field sufficient that this electric field is enough so that the theta f becomes 0. Okay, so the 0, so this is called zero barrier evaporation field, where the field, this is the field at which the energy barrier becomes 0. Okay, and this particular field where the energy barrier is 0 is called the evaporation field. Okay, we can put it as a EVAP. Okay, so this is a very important term, and this is a value which can be calculated for different elements. Okay, so now we know that in the previous expression we have a QF is equals to Q0 minus root to the power n cube E cube divided by 4 pi E naught F. Okay, and Q naught, which is the initial barrier, the initial barrier can be given as the binding energy plus summation of In to the n minus n work function. Okay, so now as I told you that theta f is equals to 0, correct. If you make theta f is equals to 0, then your theta 0 becomes root of n cube E cube divided by 4 pi E naught, and during that time the field is called field evaporation. Okay, with this you can get FEVAP is equal to theta 0 square 4 pi E naught divided by n cube E cube. So this is the expression for the evaporation field where the energy barrier is 0. So this is the field required to make the energy barrier 0. Fine. So based on this expression you can again put theta 0, this particular expression in this equation, you can write it as a EVAP is equals to 4 pi E naught divided by n cube E cube binding energy plus summation of ionization energies minus n work function. Whole square. Okay, so this is the field evaporation, and you can see that this field evaporation field changes as the charge states. Okay, so it varies. So evaporation field varies as the charge states for one element. Okay, for example, if you have a tungsten, if you have to charge state of +1, 2 plus, 3 plus and 4 plus, then your field evaporation field will also vary as 102 nanometer, 57, 52 and 62 nanometers. Okay, so the evaporation field changes as the charge state also changes for that particular element. Okay, so Brandon has made a criteria for field EVAP. Okay, is that he has defined as the evaporation field which is having a lowest value, and the corresponding charge state will be the dominant of the ions during the field evaporation. Okay, so I hope you understand what Brandon has told is that evaporation field which is having a lowest value for that particular charge state, during field evaporation that particular charge state will have a dominant among the other ions. Okay, so the most of the metals they have a charge state, they have a evaporation field between 10 to 60 volt per nanometer. Okay, so as I told you, the above model, whatever we have seen the equations, these are for pure metal. These are for pure metal, means that each atom, the neighboring atom also is same. So the bonding states will be, the bonding energies will be same. But for a multi-component alloy, for multi-component alloys, this is not true. So that's why it is not clearly defined. Clearly defined. Okay, so this is due to the difference in potential energy. Potential energy of the adsorbed atoms, that depends upon the chemistry or the atoms, the neighboring atoms surrounding that particular atom. Okay, so or the local neighboring atoms. And one more important point is these evaporation field also depends upon the crystallography. It means that, as I told you, poles, these poles, crystallography poles, are directly corresponds to the atomic terraces. Okay, so based on the crystallographic pole, either 100, 110, the atomic terraces, the distribution of atomic terraces also changes. This will have a direct impact on the field around those atomic terraces. So your evaporation field also changes based on the crystallography of that particular tip. It may vary up to 10% to 25% from one pole to another pole. Okay, so up to now we have seen the energy barrier. We have also seen how to the evaporation rate. We have also gone through the evaporation field, where the barrier theta f becomes 0. Okay. So these are the three important terms which we have understood. Now another important thing is calibration, which is called field temperature calibration. Field temperature calibration. We assume that the field evaporation is a thermally assisted process. Okay, and so from the equation, if you see field evaporation equations, which is equals to mu 0 exponential of minus theta qf divided by k bt, you can see that there is a energy barrier term and there is also a temperature. Okay, based on these two values, you can have a infinite combinations, so that to make a constant field evaporation rate, correct. So you can choose a different QF and different temperature values such that your evaporation rate is constant. How to change QF value? It depends upon your field applied, electric field. Fine. So you will have infinite combination to make it at the same evaporation rate. So for approximation, assume that for approximation, assume that the electric field value F is very close to field evaporation. Field evaporation, it is where theta F is equal to 0. for approximation, if we assume that the field value, the electric field, the actual electric field value is very close to the evaporation field, then the height of the energy barrier, which is QF, will vary linearly with field. Okay, so the with expression what we can do is QF is equals to Q naught minus n cube E cube divided by 4 pi E naught F. Okay, so this expression we understood in previously. Okay, so now what we can do is this expression we can rewrite as Q0 minus Q0 under root of n cube E cube divided by 4 pi E naught F Q naught square. Okay, you can see that if I have multiplied the denominator and the numerator and the denominator by Q naught to get this particular expression. Now, based on the expression of FEVAP, which is equals to 4 pi E naught by n cube E cube Q square, if we put this expression here, what we get is a QF is equals to Q naught 1 minus F divided by FEVAP. Okay, because you can write this particular expression as F1 by FEAP, correct. So this particular expression you can write as a 1 upon FEVAP. Kind. So you can see that the field, the barrier, the energy barrier as a function of the electric field and also the evaporation field. Okay. So what does it mean? So here this the above expression can be combined with the field with the evaporation rate, which is given by mu 0 exponential of minus theta f divided by kBt. Okay, so therefore the dependence of electric field required to field evaporate a specimen at a given evaporation rate as a function of time can be given by F divided by F EVAP is given by 1 plus kBt theta naught ln p divided by mu naught. Okay. So this expression can be given. So if you how it came this expression, you can see that if you take this expression in log scale, so what you can do is you can write this as a ln field evaporation divided by mu naught, which is equals to minus theta f divided by kBt. Fine. Now put this expression in here, so you will have a and the k and qf, you will have a kBt divided by q naught ln evaporation divided by mu naught, which is equals to f divided by FEVAP minus 1. Okay, so and this expression can be rearranged to in this form. Okay, so this is how you are getting the field as a function of evaporation rate. Okay, and this particular expression, as I also experimentally the values are matching with the values which are calculated. Okay, so this is a this is nothing but this particular, it is a relative field required to evaporate a metal at constant field evaporation as a function of temperature. Okay. So, if you want to keep this evaporation rate as constant, correct, and you have a two variables, one is field, relative field, and also the temperature. These two terms you can experimentally vary such that you will get a field evaporation rate as constant. Okay. So, based on this you can see the plot. You can the plot by Francis, which he has published in APL, where this is the relative field, this is nothing but F divided by F evaporation field, and this is your temperature. Fine. So, as the equation says that F divided by F EVAP can be written as 1 plus KBT by theta 0 ln EVAP divided by mu naught. Okay. To keep this constant, you can actually vary the field, the relative field and the temperature, and you can see that this expression, this he has recorded for tungsten, pure tungsten, and you can see that it exactly fits to a linear way. Fine. So, based on the species or the elements, the slope can vary depending upon the element of which is measured for the field evaporation rate. Okay. So, I hope that all the equations are understood. So, the most important part is all the equations above, they assume that this is a thermally activated process. Okay. So, and based on the Müller's model, which is a very simplified model to express to understand the potential energy of the atom and the ion without the field and in presence of the field. Okay. So, post-ionization. So, there is another term which is called post-ionization. This is as I think in the third class we talked about field ionization of gas atoms. Field ionization of gas atoms which is near to the tip surface. So, this is a similar phenomena which is a post-ionization. It means that if you have a needle specimen, if there is atoms which are field evaporated as ions, So, these ions which corresponds to the sample or the specimen, these ions can actually reionize. It means these directly acts as a gas atoms. Fine. So, this is called post-ionization. So, any atom which get polarized and get ionized and accelerates, but near to the tip surface, if they are present at a certain critical distance, it is possible that these ions get reionized with +2 or +3 states. Okay. So, above model, the drawback is it cannot predict the experimentally charged states of the evaporated ions above Müller. Okay. So, scientist Haydock and Kingham, they propose that when an ion leaves the surface as a single charged ion, they can actually re-ionize in the vicinity of the tip, similar to the field ionization of any gas atom. Okay, so I hope that you remember this diagram, particular diagram. We understood about the potential of a gas ion near to the tip surface. So this is your tip surface, this is vacuum, and on application of field, the potential energy gets distorted like this. Okay, this is called work function. This is your minimum potential energy. Fine. So for the post ionization, in this case, occurs at a critical distance, and this critical distance is nothing but what we call Xc for a gas atom, and this is given by Xc is equal to I n plus 1 ionization for that nth n plus 1 electron minus work function divided by the field. Okay, where I n plus 1 is the n plus 1th ionization energy, phi is the work function, and F is the electric field. So probability of field ionization is directly is field dependent. Okay, so also for a given electric field, the probability for a given electric field, the probability of an electron tunneling through energy barrier, okay. So the electric field or the applied electric field also can govern the probability of the tunneling event across the energy barrier, and this totally depends upon the time the ion spends in the ionization zone. Fine. So and this, if this depends upon, then it can directly related to the probability of n plus 1 ion depends upon the velocity of the ion, which is also a function of mass. Okay. So each atomic species, based on the mass, their velocity will change. Based on that, it also depends upon the time which is spent near to the ionization zone. So more time it spent near to the ionization zone, more probability will increase for the tunneling effect and also the reionization of these ions for the n plus 1th electron. Okay. So the variation, so what we infer from is the variation can occur in between the charge states that totally depends upon the element or different isotopes. Okay, different isotopes, we can type as a different isotopes. Okay, so based on this we have explained some fundamental equations which can be used to calculate the actual evaporation rate, your evaporation rate, estimate the field, the relative field which is required to keep the evaporation rate constant as a function of the temperature, the combination of temperature. We also discussed about the energy barrier, which is a function of field applied, and the energy barrier, when it becomes 0, that particular field we call it as evaporation field. Okay. So based on this and also we have also discussed about the post ionization post-ionization, it is nothing but the atoms which are ionized. Atoms which are ionized from the tip surface, they get re-ionized. This is depends upon the time they spent on that ionization zone, okay, and they will have some critical distance where these ionization can takes place. So that's why the different charge states can be obtained for that singular species. Okay, so with this I will end this class, and in the next class we will also go to understand the how these field evaporated ions are reconstructed. Okay, so we'll also talk about the reconstruction to mimic the exact nature of the atomic structure which was present in the tip. Thank you.